Hello. In today's video, you will learn what a chi-square test is. First, let's talk a little bit about the data that we will be using. The data today will not be real, so it is just for learning. But imagine that in a classroom-based research study, the researcher wondered if males and females prefer pair work activity differently. Maybe males like pair work more, or females like pair work more, or maybe they like it the same. So the data shows the responses of the males and females to the question if they prefer to do pair work activities rather than on their own. Now that you have a little bit of an idea about the data itself, let's talk about what a chi-square test is. The chi-square test of independence, or it's also called the chi-square test for association, tests for whether two categorical variables are associated, or this test determines whether two variables are statistically independent. The chi-square test for association determines whether there is an association between two nominal variables. It does this by comparing the observed frequencies in the cells to the frequencies you would expect, or the expected frequencies, if there was no association between the two nominal variables. You will learn a little bit more about what an expected frequency and an observed frequency is later in the video. You have a sense of what the data is, what the purpose of the research is, and what a chi-square test does. So now let's take a look at our data. Today, to teach you a little bit something different, you will learn how to import data from SPSS. Even if you don't know how to use SPSS, or even what SPS is, this might be helpful if you do end up learning SPSS. So for now, just learn a little bit about it as we move through it and realize that you can do these same things in an Excel file and import it through CSV or an Excel document and get the job done as well in terms of getting your data into R. But today we'll look at the SPSS import. Now, if you were working with this data in SPSS, you would want it to look like this. We have 3 columns. The first column is whether or not the group is male or female. The second column is whether or not they prefer pair work, yes, or they don't prefer pair work, no. And the third column is the observed frequency of each participant in that group. For example, for females who don't prefer pair work, there were 15 total. 15 people in this group. For males who do prefer pair work, there were 18 people in this group. Now, this is how you would make it look if you were working with it in SPSS. But for our purpose, we like to make it look like this, which is something closer to a frequency table. Frequencies are how many participants are in each group. We want to make it look like this in order to import it into R. So what I very simply did was just take the numbers here on the left, 18, 7, 10, and 5, and put them in this format. So these two tables represent the same information, just in a little bit of a different format. Here you can see that 1 equals male, 18 count, prefer, pair work, 7 don't prefer it, and then for females it's 10 and 15. So this is the file that I'm going to import into R. In order to import that data, first install this package, foreign. I've already installed it, but you can pause the video and then take the time to install it if you need to. And then load that package with library foreign. Here you can get the lookup path. You can get the path to the file on your computer by calling this code and saving it to a variable. So file.choose will bring up a dialog box like this, and you can maybe look at the desktop and then choose that file. I'm going to go ahead and choose it. And I know that this is the one I want. So take a moment to look up the file like we just talked about. And it should look something like not this one, but the other one. It should look something like this to remind you. Take a minute to look for that file on your local computer and import it and save the path to a variable like lookup file. And then we're going to give lookup file the path to read.spss is the function that's going to import our SPSS file, and then we want it to be a data frame whenever we bring it in. Because we want it to be a data frame that looks like a frequency table is why we changed the way that the data looked a little bit in SPSS before we brought it in. Now save this imported data frame into a variable. You can call it frequency table or something like that. I'll call that code. First I need to load foreign, and now I'll call that code. And here we go. So we have pair work, no pair work, and here's our frequency table just like it looked like in SPSS. So R has done a good job of bringing that data frame in for us. Now that we have our data to work with, I'm going to minimize or make smaller this heading. And do remember, please make these headings and type along with the video so that you can refer to this later. If the video goes too fast at some point, please just pause it, go back, and you can copy down what I've typed. After you import your data, let's quickly talk about the assumptions of the chi-square test. The first assumption is that you need two categorical variables. A categorical variable can either be nominal or ordinal. And even though you can use a chi-square test for association with ordinal variables, they may have to be treated as nominal variables, losing their ordered nature. Here in our example, we know that we're working with two nominal variables. In fact, they're dichotomous. So we're working with a variable that is either yes pair work or no pair work, and either male or female. The second assumption is that you should have independence of observations, which means that there is no relationship between the observations in the groups of the categorical variables or between the groups themselves. And the third assumption goes back to something you learned at the beginning of the video with the expected frequencies or the expected counts. So this assumption relates to the nature of your data in order to provide a valid result. All cells, and in this case, each cell is one of these 4 numbers. You might have more data in a different study, so you'd have more cells. Here, all cells should have expected counts greater than 5. Now, these are not expected counts. These are the raw counts that we looked at. These are your observed frequencies. So these are the actual frequencies that we're bringing in. However, we're more interested in the expected counts for the assumption number 3. Later, you will learn how to find the expected counts for each cell. Okay, those are our assumptions. Now I'll minimize that one. And minimize means make smaller, so I'm just making it smaller. And next up, for the chi-square test, let's run the test. So we'll get our statistics. The actual R code to run the chi-square test is very simple. So the difficulty with this test is not so much the code, but understanding what the test does, I think. The chi-square test dot test, and then you open parentheses, and here this is actually not what the file's named anymore, so I named it something new here. Now it's called frequency table. So I want to change new file to frequency table. And then set correct equal to false. You can do some research on your own to understand why correct equals false here. And then we save the result of this to a variable. And when I run both of these lines of code, I get Pearson's chi-square test, and I get my p-value, my degrees of freedom, and I get the value of my chi-square statistic here, my Pearson statistic, which is 5.148. Now with this test, if the p-value is significant, if it's less than 0.05, then that means that our nominal variables are dependent. If it's greater than 0.05, it means that they are likely to be independent, and therefore they're unlikely to be associated. So here we can see that we're less than 0.05, so it's likely that our variables, which are gender and preference of pair work, or how much each group likes pair work, we can see that since it's significant, there's likely an association between those 2 variables. We talked about the third assumption earlier about expected counts, and the code again for expected counts is easy. So you take the variable that you made and saved your chi-square statistic in. You take the variable with all of those 3 pieces of data, and then you call $ expected on that variable, and we'll save this into expected counts. So I run that code, and then I show what I've run, and you can see that here the numbers are different than they were here. So here in our observed counts, our observed frequencies, we have 18, 10, 7, and 15, but in our expected counts, we have 14 and 11. In order to meet the assumption, each one has to be greater than 5, and we can see that they are all greater than 5. If you did not meet this assumption, there are other options that you can take in order to do similar tests. We won't cover those options in this video. Now that we have our expected counts, let's look up phi for effect size. So we want to have an effect size to work with here. Install the package psych and then load psych. Now, when I was making this video, I ran into a little bit of a glitch, I think, with the code where we use phi open parentheses and then we put in our data, and it is meant to give us the phi statistic afterward for effect size. I ran into a glitch, so I figured out a workaround. Whenever you're writing code and you're doing technical things with computers, there's going to be a time maybe when you even have a hard time figuring something out, and you'll figure out a way around it. So ideally, or it would have been better for me to just use what I did earlier, the imported frequency table, but it wasn't working, so I figured out something creative to do instead. Just keep that in mind, that that's okay for this video's purpose. It might not be okay if we were working with a much larger amount of data, but right now this solution works. So because I had a hard time feeding in this frequency table to this function to get the effect size, I just made a custom matrix, which I know this function is supposed to take a matrix. I made a custom matrix that is the exact same as this data frame that we brought in. And this is the code that I used, and you should be a little bit familiar with this code because you should have learned it in an earlier video. Even if it doesn't make total sense, I can explain it now. So I'm making a matrix, and then in that matrix I have C open parentheses, so this is a vector. And then I have my 4 pieces of data, 18, 10, 7, and 15. And then I'm saying I want 2 rows. So whenever I run this code, it's going to give me, and I can show you what custom data looks like. So here we have 18, 10, 7, and 15, and 18, 10, 7, and 15 inside a matrix. So they look very similar, but for some reason this matrix works inside the phi function, so that's why I'm using it. And then I run the code to get the phi statistic, and then I run the variable, and the phi statistic is 0.32. That wraps up the bulk of the code for doing a chi-square test. At the end, again, so that when I come back later, maybe I can just highlight this whole section if I come back at a later time, run all the code at once, and this code here at the end would give me everything I need to use this code maybe in a write-up if I'm writing a journal article. I can just hop in to R, run all the code, and I'll know the last 4 things that come out of it are all I need to see, because I already know that the other code will work because I made it work whenever I wrote it. And here you can see these last 4 pieces are my frequency table, are the numbers that perhaps matter the most, which are my p-value and the Pearson statistic, and then our expected counts to make sure we have that assumption met, and then our effect size for a 2x2 table that involves 2 categorical variables.